the language of the universe.
But I don't understand it.
Yeah, but it uses Nabla. Like
Yeah.
it's connected with Nabla. I'm saying separate.
Oh, like if the
Like, you make it, like, separate things.
like if it was not connected to Nabla anymore.
Yeah.
But in some way, the whole definition relates to Nabla. How would you define that without Nabla?
I don't know.
What? How can you define?
That's what I'm saying.
Okay.
In your head, you're
No, but
like,
no, no, no,
oh
but
yeah,
no, no, no.
obviously.
But you can switch out variables. You can't switch out operators though, because like
I mean, why not?
because the definition of a divergence or the
Change the definition.
Okay, that's just. Well, then it means something else though. That's what I'm saying. Then
No,
it's
no,
something
it
else.
doesn't.
Then that's not a
no,
curl anymore.
No,
If you're changing the definition
I'm
of
saying-
divergence, that's not divergence
I'm saying
anymore.
it's the same thing, but you write it down differently. You write it down differently. That's
I
all I'm
wouldn't know
saying.
how to even think of that. I wouldn't even know how to think of how to do that differently.
Okay, pretend A is B.
No, but what I'm trying to say is if like the only way to define divergence or the way that it's defined is in terms of how it's moving in all these directions, which then in turn is defined the only way by the gradient operator, by its respective derivatives. So in this case, you can't just change the definition of this divergence and not use gradient anymore because the literal meaning of divergence depends on how these things are diverging.
No, I know.
which then
I'm
depends
saying
on
the
gradient.
the meaning is the same thing, but you write it down differently.
Okay, I don't know what you're saying, bro.
Imagine Nabla is not a thing. It's
but
not a
but
thing.
dx dy dz are a thing,
Sure.
of course.
But maybe those are written down differently too.
So you're just saying like different ways of representing it.
Yeah.
That's okay. Obviously, that's different. That's just like notation.
That's exactly what I'm talking about.
Okay, that also helps. Okay, I guess.
We were talking about
I
notation.
guess too. Okay, whatever.
Anyways.
Yeah, notation is important, especially coming back to that quote where mathematicians can mainly just kind of agree with themselves. I don't know if.
Oh yeah, no. The point I was trying to get to
Okay, yeah.
is actually that the fact that divergence and curl and gradient are all combined with this gradient operator, to us makes perfect sense, right? Why? Because mathematics is written for
Mhm.
mathematicians. To somebody else, what do those things have anything to do with each other? It uses the same symbol in some weird combination, but it
Yeah,
to them it looks the same, but to us it does something different,
something different.
but connected in a deeper sense.
I feel that. I
Yeah,
feel that. That's powerful.
Yeah, I guess that's what
That's
I was
also
trying to get
sometimes
to.
when you can like misuse notation, like abuse notation, where you use the you use the same thing.
Yeah,
Like Nabla,
yeah,
like Laplacian,
yeah.
like you know that like they all
Yeah,
use the
yeah.
goddamn same thing.
Yeah.
And then you're like, what is doing what? And only a mathematician or like or like you know
Yeah.
what I mean, like that person who is related with that topic would be able to understand.
But that's also
what operators.
that's
being
also
used.
really useful though. Like if you understand the content to where you can like accurately abuse notation and other people understand what you mean, then that's fine, right? Like doing Nabla squared. What does that really mean? You know what I mean? What does that really mean? What are you doing? You're abusing notation by doing Nabla squared. We interpret it as Nabla dot product Nabla. But at the end of the day, you're dot producting two operators together to make a new operator. And then like that just
it gets very notationally important where you would need to know the fundamentals to truly get to know what that means. Like
Yeah.
to truly understand it.
Yeah.
Right.
well,
I think we will switch the episode a little earlier, and maybe this will be part of the second part because
Really?
I think I kind of want that. So if you're listening to this, I hope it's on the second part because I think it'll be really cool if we just stop the first episode, like when we say something really intriguing, and they're just pop.
All
next
right.
Episode. So we can just start with the next.
Yeah.
Okay. So if this is the next episode, which it should be, welcome back. We're continuing our part on history of physics, talking about Copernicus and Leonardo da Vinci. And on this one, on this part, we're talking about two new individuals that you've probably already read in the title. So hold on. What were we talking about? Yeah, we're going to continue the conversation. We're just going to continue it like it's another part.
Yeah. Well,
Yeah.
we were talking about notation, but I think we kind of finished that a
Yeah,
little bit.
notation is important. Copernicus is cool. Da Vinci is also cool.
Mm-hmm.
Copernicus has some good quotes. So does Da Vinci.
Mm-hmm.
You know. Now we can move on to our other two individuals for the night.
Well, astronomy.
Astronomy. Yeah, that could
The
be
stars.
That could be basically this part of the podcast.
Planets.
Yeah.
And pulsars. Bars. So, the person I wanted to bring up next, Galileo Galilei. Crazy guy. He's got some really good experiments, observations, and inventions under his belt. He was actually born 1564, so almost 100 years after Copernicus. And so he was born in Pisa, in Italy. And he went to the University of Pisa. And famously, very famously, he's known to strongly agree with the heliocentric model of the universe, which makes sense. Do you think you would have been a supporter at the time?
It would be questionable because it's, I don't know. Would you?
To be honest, I'd like to think so.
Yeah.
I don't know if the risk reward factor would be worth it though, to have the church on your back. You know?
That's the only thing, right? Do you your opinion, if it holds any ground, might stir some other people up.
Exactly.
Which might entail bad stuff's gonna happen to you. So yeah, it might not be the cleverest idea, because actually, interestingly enough, was it? No. I'm forgetting. It was either Galileo or it was Kepler, who it was one of them that kept their papers till the very end of their life.
I thought that was a Newton.
No, Newton just did that because he was a little bit of an idiot. But I'm saying one of them basically kept
I think
a lot of their...
Copernicus did publish something as he died.
Yeah, because I know that one of them basically was keeping their papers till their end because they knew that it would spark a lot of controversy if it ever kind of came up. Because obviously, they held a lot of... Because if you remember, if you make scientific discoveries and then you're like, oh, this is true, and everyone's like, oh crap, oh no way, and then you're like, I'm just gonna break everyone's understanding of reality. You're like, oh, hold up, wait a minute. Even though you believed everything else, this is no, this breaks my reality. That I just didn't know about. This breaks my reality. I can't believe that. That's their understanding at that point. So I don't know if I want to get in. I don't know if I want to get in the middle of that.
So Galileo, strong supporter. Famously, he built a telescope. He was, one of the grandfathers of precise astronomical observations. Because realistically, you can only do so much with your eyes. And, you could sit there as long as you want and look at the stars and I don't know how, but measure the positions. How would you even do that? Measure the positions of the stars with your eyes?
I guess it would be just a guess. Just hey, that looks like... No, I don't even know. I don't even know how you would start. I don't even know how you would start.
But yeah, the point is that Galileo had enough of it. And he took matters into his own hands. He obviously did some research into optics. And optics is super, super interesting. Especially it's interesting now because there's a field called quantum optics, which is, I feel like I want to relate everything to quantum mechanics because it's just so there. Everything you do technically has quantum effects that are just very negligible.
Mm-hmm.
And just
I guess, I mean, at this time though,
just a real 1 minute talk about quantum mechanics. Photons carry energy, right? Photons allow you to tell where things are with your eyes. We know now that photons are these discrete particles. Well, they're absorbed discretely, but they live in this like wave nature / particle duality realm. And everything breaks down when you go to the fundamental level of observations. If you try to observe something one photon at a time, automatically you're going to run into some problems if you're assuming a classical world, because photons don't behave classically. Mm-hmm. Now, in the realm of quantum optics, now this is like very on the surface, but you study like the polarization of photons, which, what an insane idea, right? That you send an unpolarized photon through an analyzer and you make it vertically polarized. And then you send it through a 45-degree analyzer. And the photon has to pick with a 50% chance whether to transmit or to not transmit. Insane.
I don't know what does that have to do with anything. But
No, this has to do with optics.
okay, I think a very interesting thing though at this whole time was that all of these individuals were so interested with the big things.
Yeah, that's true.
You know what I mean?
That's
like,
true.
No one's even thinking about, like, as you were talking about, I'm just like thinking in the mind of someone living in this age where everybody is talking about the stars, the planets, the sun. What about?
I feel like that's not true.
What do you mean?
People were definitely thinking about like chemists back in that time. If chemistry was a thing, was chemistry a thing?
We just don't know enough about chemistry. It definitely was.
We
It
don't
definitely
know.
was. It definitely was.
But what, like, you know?
No, because matter.
Exactly.
Matter had been.
But if chemistry was a thing,
matter.
if chemistry was a thing back then they were seeing these like weird reactions, and then you're asking like, why? Why does it react this way? It obviously has to do with what the thing is made of. So clearly they were trying to investigate the smaller divisions of matter.
The atom was discovered in the 1800s. That's like 200 years after this.
Yeah.
So long time. So that's what I'm saying. So maybe they had like ideas about, okay, this is happening, but they did not have the slightest clue about what to do with that. You know, like what I'm just intrigued by the fact that they see these planetary bodies. I guess they're much more visible than atomic bodies, but you see these planetary bodies, and obviously your first thing is hey, let's observe them, let's classify them, and let's deduce things from these, and not instead look at our own planet.
You know, it's insane though.
What's that?
If light were to be like continuous and not discrete, then quantum mechanics would just not be a thing.
I don't think the universe. What?
I mean, this is
a lot of things.
This is under
happen, though.
Right. This is under the assumption that we are alive right now.
Okay, sure. Light just somehow.
But if we discovered that light were actual just waves and not discrete at all in any sense, then quantization of energy is just not a thing. Because you can just divide as much as you want. Now there's no such thing as discrete energy levels. No such thing as spectral emissions in atoms. No such thing as quantized angular momentum or anything like that.
It would be a crazy world.
It would be a crazy world.
That'd be a crazy world.
Might be an easier world to live in though. Because you describe everything classically and then it just works all the way down to the bone. And then you got everything figured out.
That'd be pretty classic.
Okay, back to telescopes. Because telescopes are crazy inventions.
Because telescopes also tie in with the other guest of the night, Johannes Kepler, who also made significant discoveries in astronomy, continued, the Kepler's three laws. Keplerian telescope was invented by him. Just a little bit different from the original Galilean telescope. We can talk about that. But yeah, so even he was super into the night sky, right? Like just observing things. And interestingly enough, he was not the individual I don't think if anyone knew this, but he was not the individual credited with like discovering and cataloging all his stars. That was actually his he was his assistant, so I'm assuming like his supervisor or whoever. That was named Tycho
Brahe. I don't know.
Tycho Brahe. Famous guy. For 20 years, this guy was observing stars.
Wow.
And he cataloged stars.
Wow.
Stars' motion, all that kind of stuff through the telescope, right? Through a telescope that was very, very obviously not sophisticated, not even close to this day and age, but he did it through his way back in the day, through obviously the closer stars. And through that catalog and that knowledge of stars, Kepler was basically able to, or it helped him formulate his famous three laws of motion, right? So yeah, telescopes make a lot of this possible.
Now, what is the point of telescopes? So if you think about it, the point of a telescope is to make your eye bigger.
It's basically a very fancy magnifying glass.
Yeah, well, you want to increase the amount of information that your eye can absorb. So a telescope is usually a tube, right? Or at least in this case, the refracting telescope.
Or even the reflecting telescope.
It's a big tube. And you can imagine as if the opening of the tube is your pupil, but just dilated up. And so imagine if your pupil was that big, just how much information can enter your eyes.
Because if you think about it, because remember, reflecting telescopes weren't a thing at this time. So if you think about it, the only, like, your eye itself is a lens, right? So we think about things coming in or converging or diverging as in terms of, because we understand lenses at this point. We understand how light moves through lenses. That's a well-known thing. So if we think about, I don't know if this is how they thought about it, but this would be a really cool way to think about it. Because if you think about how your eye works, it's a concave lens. And what that does is it basically converges the light rays onto a singular point, the focal point, where your retina stays. Or no, not your...
I don't know.
Very good with biology. Something stays there. And it basically concentrates on your retina. No, it's your retina. It concentrates on your retina. And that's the idea of your eye. So if you want to look at something much, much farther away, you can just think about it. Like anything really far, your eye can't really deceive. So why don't we make a bigger lens? Discern. Why don't we make a much bigger lens that can hopefully take in a larger, number one, field of view, and also get very, very, very far objects, right? And like that was kind of like the first premise. I mean, I don't know if they thought about it like this, but that would be really cool.
Do you mean smaller field of view? Because
no, technically for the sky. No, of course. Yeah, no, of course. Yeah, sorry. Of course, much smaller field of view compared to the eye. But I'm saying like in terms of the telescope. Yeah, sorry. So in terms of the eye, obviously you're concentrating your view because of the larger lens. But the advantage of, number one, just this idea is that, hey, if my eye can converge light onto one point, why can't I just make a bigger eye? I don't know if that's how they thought about it, but that would be really cool.
So refracting telescopes.
Because he wasn't the first, right? Galileo wasn't the first to make the telescope, the refracting telescope.
I think he was.
I don't think he was the first.
Okay.
I think he was like a guy that did. Okay, just continue on talking about his telescope contributions. Maybe I'll.
I was just gonna say how like refracting telescopes work.
Go for it.
So there are actually two lenses. The first lens is this is the Galilean refracting telescope. Other refracting telescopes can be made a little bit differently. But the first lens was a half concave lens. So the first side of it was convex. half convex. Wait, am I getting this backwards? Convex is when it's like this, right?
Yeah.
That's convex. Concave is
Yeah.
so,
Yeah,
okay.
yeah.
So yeah, convex. Now in convex lenses, those converge the light rays.
Oh wait, then I said concave when I was talking about my eye. Oh, I'm so
Yeah.
sorry. Oh yeah, convex. Oh yeah. You're right. Shoot. My
So
fault.
yeah, so the first lens converges the light rays closer together. And then the second lens is a concave lens, which actually disperses the light. I don't think disperse is the right word, but it essentially separates the light.
It refracts the light.
Refracts.
Yeah, it
Yeah,
refracts the light.
It refracts the light. And so what is it now?
But
Telescope.
where is this lens placed is important. Is it? It's not at
Well,
it's a little because it's not at the focal point, right? Because
no,
the
it's
way,
after the focal
exactly.
point.
No,
yeah.
no, isn't it before? Am I
No, it's
tripping?
it's after.
Okay.
Yeah, it is after.
I swear after was Keplerian. Am I tripping?
I have the diagram in front of me.
Oh, it is.
Yeah, it's right there.
It is after.
Yeah.
No, that's Keplerian, bro.
Oh,
This guy's reading the wrong telescope. That's what I'm saying.
Anyways.
That's Keplerian. So yeah. So
they all work the same though,
I
like
mean,
essentially.
No, the whole point
Okay,
of the
well-
Keplerian is that it's different.
Okay, well, what?
It's better.
Okay, one of them is before the focal point. One of them's after the focal
Yeah.
point. But I'm just trying to explain the telescope itself. There's two lenses. One converges the light rays. One refracts the light rays. Essentially, you can take a big image, and the convex one makes the image smaller, and then you have a smaller concave lens, and that just separates the light rays so that they hit your eye, and then you can see all the information that was in the view of the big tube. So yeah.
Basic
What,
telescopes.
do you know the difference between?
Yeah, so I was kind of
Yeah.
going back and forth with them, and basically like the Galilean telescope diverges the light rays on the second lens, like it comes in and goes whoo, right.
Yeah.
The Keplerian telescope converges the light rays on its second lens, and it's done after the focal point, right? So number one,
It converges after.
converges. So number one, yeah, because think about it, right? Because it's going out and then think about it, right?
So there are two convex lenses.
No, there's one. Okay.
Oh
actually,
yeah, no, there are two. Yeah, wait,
What do you mean?
there are two convex.
Yeah.
Yeah.
In Keplerian.
Yeah.
In Keplerian. Yeah,
Yeah.
exactly. In Keplerian, there are two convex. In Galilean, it's a convex and then a concave.
Oh.
So in
So
Galilean,
Keplerian was probably better then.
yeah, Keplerian is
Yeah.
better. So in Galilean telescopes, you get the light. And okay, again, for those people that are not seeing the podcast, I guess my hand doesn't mean anything. But basically, the light rays are, as they're converging towards the focal point, you basically put a lens right over there in the middle. I mean, not in the middle, but you basically put it before the focal point, such that it hits it and diverges to your eye, right? And the Keplerian telescope basically hits its focal point, so the two light rays basically intersect, and it then hits a lens, which then converges the light rays into your eye.
So yeah, the difference here is that if the light passes the focal point, then the image inverts.
So that was one disadvantage with the Keplerian telescope, that, hey, your image is inverted. But the advantage is that you actually get a much wider field of view. And really know the physics behind it? Like, I mean, is it...
No, I haven't studied telescopes
I've
at
really
all.
studied this. Again, it was just like a research study before the episode.
I just know like the effects of
Yeah,
lenses.
like again, because
and it
number
makes
one,
sense.
I know the image looks better on a Keplerian telescope, and number one, you get a larger field
Number
of
two.
view. And
Yeah.
and number two, and you get a larger field of view than the Galilean, simply
Yeah.
because of the lens placed a little bit after. Again, the physics behind it, I'm thinking about it, like, as I'm saying this, which should not be done on a podcast. Like, I should definitely have this thought about before, but I'm thinking about it, like how it would widen the field of view. And the only thing that I can think of is that the concave lens in the Galilean telescope.
It has to be placed closer to the eye, right? I'm guessing, because if it diverges the light rays, then you're gonna be missing a lot of the
So it has to
outside
be placed.
light
So
rays.
like, because also you're cutting off a little bit of that, and then you're also diverging the light rays that are not all coming to the focal point.
Yeah.
In this case, in the Keplerian case, you're converging all of the light rays that come onto that point. I don't know if that's a good explanation. If anyone has a better one, feel free to message us. I'll be very, very inquisitive to listen, or very, very intrigued to listen to that. Because it's interesting. Because, I mean, I was doing a little searches here and there, and I never really got a concrete answer. But it was basically around, like, hey, because obviously the Keplerian telescope was made after the Galilean telescope. So I don't know why you would make the same thing but worse. So I would just assume it would be better. Also, I searched it up.
The image was clearer.
The image was clearer,
For
but
sure.
again, it was inverted. So actually, what was done in modern day Keplerian telescopes, like if you want to kind of simulate it, is they would put a prism in between the lens and the eye to flip back the image. Yeah. So, and that actually made it really heavy, and like it's a little bit of a disadvantage now because of that. So like if you're comparing them 1-to-1, like a Galilean is a lot lighter than a Keplerian, but again, Keplerian has advantages here, this one has advantages here, right? So it's kind of a here and there, but these telescopes are basically kind of what define these individuals in terms of their, or I guess not Kepler, but in terms of Galileo, it kind of defined his whole mark on science. Also, 1 year prior to Galileo's invention, the telescope was invented. 1 year, just 1608, this one guy invented it, and then 1609, Galileo invented his.
Yeah.
So just a little bit late. So they cool.
Well, what did Galileo actually do? Well, he first of all observed the moon. I think I would do that first as well if I just invented the telescope.
Yeah.
It's like,
The moon, I think, is
the
the
moon.
Yeah,
it's
I mean,
like
that's
the
the
biggest
closest.
thing in the sky at night.
Isn't he the guy that also discovered that I might be wrong, that the stars are not as close as we think? Because that was
I think so,
Someone.
but that's just
someone in this era.
you can do that. Like as soon as you have a telescope, you can basically figure that out.
Yeah, because
So he might not have been the one.
Because again, with the geocentric and that, like with that whole model as well, like stars were not thought about to be that far.
Yeah.
Like stars were just thought about to be like, oh, it's just one planet size away kind of thing.
Yeah.
You know, so they didn't even think about it. And also Da Vinci also noticed and stated, again, this is going back, but Da Vinci also stated that the sun is, I'm going to paraphrase here, but is radiant and is hot, which is something that, again, is like, oh, it's an actual being.
You can
but
tell
like,
if you're outside during the
I
day,
guess
you
so,
can
and it's
feel
just
the
hot.
heat.
I guess you're right.
You,
But
you
again,
step in
he
the shade
formulated
and
it.
it's cold, or you step in the sun and
I
it's
guess he
hot.
formulated it, but like the way he was talking about it was like, I don't think it's possible, number one, for it to just be in orbit of something like us, especially like with other stars. So anyways, I just wanted to bring that in because I thought one of these astronomers had done that, because I think one of them did. And it's really cool. I mean, who knows? My phone went off. Yeah, we're just gonna continue using that.
So first of all, he observed the moon. He found out that it wasn't smooth, and he does have these like famous drawings of the moon. It's like the first like detailed drawings of the moon.
Damn.
He did that.
Did he do like craters? No.
Yeah, totally. Well, not like the small ones.
Yeah, no,
the
of course, but
the
like
big ones,
relative.
Yeah. And also he drew like the channels on the moon, like the lines.
Yeah.
He drew all of those as well. Yeah.
That's pretty precise. Yeah.
And I actually have a telescope at home, and you can actually see the moon very well. I actually have a picture on my phone. I'll show you after. But it's a very cool sight, because you look through the telescope and you're like, damn, that is literally the moon that I'm looking at with my own eyes, and it looks so detailed. It was crazy. Anyways.
Yeah, the moon is a very interesting object, especially if you're a first person with a telescope.
Yeah.
You know, you're like,
yeah, that'd be
imagine,
really
like,
cool.
Come on.
Yeah.
Like, you have this crazy device. You're like, imagine how many girls you can pick up. Like, yo, you want to look at that? I'm just saying, like, that would be like the talk of the town.
Yeah.
This guy has a telescope. You can see the moon.
Yeah, no, that's definitely
Come on.
It's definitely a very like
OP.
like a popular thing. I feel like in his town he was known as like that guy with the telescope, but also I don't think he was letting that many people look through it, you know, like it's
I don't know what kind of person he was,
but I mean in general, like if you have this very I know, but I'm saying if you think about it, it's like this very expensive tool
Yeah, I guess
that he
you're right.
built
At
with
that
his
time,
own hands.
Because these lenses must have been so
Yeah,
expensive,
so
man.
hard.
Because lenses these days are like, okay, well, obviously these days, but I'm saying like back in the day to even construct a lens
Yeah.
might have been quite expensive. So I can definitely imagine, especially with the size, because I believe the Galilean Telescope, the
It's
first
3
one was,
feet. 3 feet long.
how wide was it?
I don't know.
Like how wide was the lens? Do you know?
I don't know.
Because that could probably be important because that usually tells the price of the lens. Because that can be, because even like the thickness. Oh man, there are so many things about telescopes. We can literally like if we do enough work, we can literally make an episode on telescopes.
No, we could.
Like the amount of different properties.
Oh, we should just
of
get
lenses.
a guest on for that.
Sorry.
We can get a guest on.
We could get a guest
That
on.
would be really cool.
Could get a guest on.
That'd
Because
actually be cool.
like the number of properties for like the lens, for like the mirrors, for the diameter, for the focal length, for the type of mirror, it's all so crazy. Especially these days with modernized telescopes. Even like refractors have mirrors, even reflectors have refractors. Like they're all basically one best telescope almost. So you can like pick and choose, but there's so many options. So telescopes are definitely really cool. And yeah, I mean they really advance science.
Okay, I'm gonna move on.
I'm gonna move on to Kepler, man.
hold on. I
sorry.
hardly said anything.
Oh, I thought
yet.
you were gonna say move on.
No.
Like, okay. Continue.
So he was the first to observe Jupiter's 4 largest moons.
Wow.
Clearly impossible to do without a telescope.
Can't even. You can.
No,
Yeah. How would you even?
unthinkable.
How would you even?
Which, if you think about,
Wait. This was probably the first discovery that another planet also
yeah,
had moons.
definitely,
Damn.
because there's no way you could tell without a
Yeah.
telescope.
100%.
No way.
100%.
So he found the 4 largest ones. I'm pretty sure he also was the first to observe Saturn's rings. I think we spoke about that.
I think we did. I do
earlier.
recall this.
Um,
Wait, which planet has like 67, 69 planet? Like which 69?
Jupiter.
Saturn. Satellites. Jupiter. That's
Jupiter.
Big one.
Yeah,
Damn.
for sure,
It's like.
for sure. Yeah,
Yeah, because how can it be Saturn? Yeah, it can't be
Yeah,
Saturn.
no,
so
it's
you
not
keep hitting it.
That's fine. So Galileo's proof of heliocentrism.
Okay, let's hear it.
Here we go. Now, heliocentric model of the universe. We have the sun in the middle, and then we have a couple planets in between the Earth and the sun. Now, what happens to a planet that's within the orbit of the Earth? Well, we'd be able to see that planet on any side of the sun. We'd be able to see it on the left, the right, in front, behind. Now, similar to the moon, when the moon is orbiting the Earth, we see the sun illuminating one side of the moon and keeping the other side dark, and we have phases because of the angle at which we're looking at the moon.
Mm-hmm.
Theoretically, this would be the exact same thing with Venus, because Venus would be on the left side of the sun. We would see a half planet. I was going to say half moon, but we would see like a right half illuminated. If it's on the other side, we see the other half. If it's in between the sun and the Earth, we would still get this like outer glow, but it would be kind of like a planetary eclipse. Is that the word? Planetary eclipse? Yeah, good enough. So yeah, he actually observed the phases of Venus, and he's like, hey, we have proof that there are other planets also orbiting the sun. So, there you go.
Dude, damn.
There you go. We have proof.
Wow. No, that's definitely
He also
impressive.
observed stars that were not visible to the naked eye. And he also showed that what we see as the Milky Way, because back then you could see the Milky Way if you're in a city.
I mean, not, yeah, back in the day.
Yeah,
Back in the day.
you could see the Milky Way. And people just thought that was space colors. But actually, he showed that those are all just a lot of small stars put together that makes that glow, that galactic glow.
Wow, that's very interesting.
Yeah.
That they could still, kind of make kind of summaries, I would say, on a galactic level. just with this kind of stuff.
Mm-hmm.
That's pretty cool. That's definitely really cool.
And yeah, the last thing is he found Neptune, but he didn't.
Oh yeah, that's a.
He didn't think it was a planet at first.
Oh.
I don't think he ever thought it was a planet, but he noted it down, and then I guess someone else
Was
chimed
like,
in.
hey, that's. Wait a minute.
Chimed in.
Wait a minute. That one's right there.
Yeah.
That must have been fun. So, Kepler, very similar to Galileo in the sense that, he was also highly related to optics. He's with light here and there. He actually, believe it or not, even though Galileo constructed the first telescope, or quote unquote first telescope, Kepler actually formally wrote it down scientifically. He basically showed how the light rays pass through the telescope. That whole crazy diagram that you were showing was basically Kepler's diagram of the telescope for the very first. And that was the Keplerian telescope. And that's how he basically interpreted the light kind of converging and the light basically coming into the telescope from wherever it was. Right? So Kepler basically, to start off, German, also a polymath, I guess, because also, all these guys are involved in a lot of different sciences. Interestingly enough, Kepler was a very fond believer in religion, and he actually went to university for theology, interestingly enough. And believe it or not, also a fond member of the astrology club.
So was Copernicus.
Yeah.
Yeah.
So at that time, there wasn't a lot of money or interest in astronomy. Like, who the hell cares about
why?
stars? Because
I feel like the kings were.
What they cared about is astrology.
Wait, I actually read
what
some.
What they cared about was, what does that star being there mean for me? They don't care about what that star being there means. True.
But that's what I was gonna say, that the kings would sponsor these astronomers to find planets or find things and name them after the kings or something like that. Just to have the honor of having your own thing. So they would sponsor research.
Kings would still be interested. I could still see them.
Well, obviously interested. Not in the science. They don't care about the science. That's what I'm saying.
The scientific aspect was not really interesting.
They just care about the coolness.
So Kepler, interestingly enough, was a huge advocate for astrology, and he was reading people's horoscopes here and there, because he was quite the talk of the town. Because also, remember, he understood the actual meanings of the stars and the planets and what where they were, or the meanings or the lack thereof. But in some sense, because he was still rooted in theology, he was still a very God-fearing person, I believe. So that's why, I'm assuming that's where the astrological aspect came from. So he was actually quite a big thing in astrology, even though throughout his entire career, he was still promoting, not to listen to astrology like it predicts your life. He would still refrain from stating that this is the way the world works. He would never, he's not stupid. He says hey, this could be cool. If this affects you, that's cool. If this is how your life is going to work, cool. But that's not actually accurate. That's just your feeling towards this particular situation. So that was basically a little bit of Kepler and a little bit of what he did. But obviously his biggest contributions to the world of science is his 3 phenomenal laws of planetary motion. Phenomenal laws.
I agree.
Of planetary motion. Kepler basically observed these bodies and was hey, let me just make these deductions on them. That's basically what he said, right?
Is that what he said?
That's basically what he said. And he's let me think about how I would describe the motion of these objects around, the sun. Because at this point, it was just 100 years after. It wasn't still common ground, but people were starting to believe in the heliocentric model, because they're hey, you know what? Now that we have a telescope, maybe it's a little more accurate. You know, were sunshades? Probably. Like, could you see the sun at that time? Like, if they had like those proper UV filters, probably not. Because like right now to see the sun, you need like a UV filter. Like you need a proper filter. Probably people died. People definitely got blinded. Not died. But people definitely got blinded.
Yeah.
Because I know there's a story, I think. There's a famous story with one guy getting blinded because he accidentally looked at the sun. I swear this is a history of physics. I'm getting a deja vu right now.
I used to look at the sun as a kid. Not for long.
With a telescope?
No, with my...
Okay. That's what I'm saying.
No, not
that's
a
what I'm saying.
telescope.
It's with a telescope where it kills you.
I'm just saying,
where it
like,
blinds you.
I would look at the sun for like 5 seconds and I'd be like, wait, this kind of hurts.
So the very first thing that this guy comes up with in... How long did it take? I think it took him 10 years, I believe, to formulate the first 2 laws. And these were known as the Kepler's laws of planetary motion at the time. And that was only the first 2 laws of motion. And that was basically, number 1, that, hey, the planets move in ellipses, in ellipses. And this was through observation, data, and just collection also from his again, I don't know if it's like professor or like from his supervisor or whatever, as I was mentioning, but that Tycho Brahe individual is where basically he got his data and he kind of was like, hey, it kind of looks elliptical, or not looks elliptical, but it follows an elliptical shape. And obviously with that, he was also intrigued in the geometry of ellipses. So he didn't come up with it, but he was describing them as with the sun as one of the focus. So one of the focal points of that ellipse, or the focal point of that ellipse was the sun, basically. That was his idea of how these planets moved. Again, he didn't still really understand, like, you know, like planets get faster and slower and stuff like that. Like he didn't really know the distance.
Isn't that a part of it?
Like that. Well, that is the third law, right? Where the T and R get related. Oh. So that was actually a little bit later. But the second law, no, I guess he did. No, because that's actually the second law. Because I guess he would know that, because the second law is basically equal areas, equal time.
Yeah, so he definitely
So I guess
knew.
he did know.
Yeah.
I guess he did know then that
he did.
planets do speed up at certain intervals and slow down in certain intervals, and this is all contained in this shape of an ellipse, right? And if you also think about it, the second law literally will not make sense if the planets don't move in ellipses. Because the second law basically states, again, that these planets sweep out equal areas in equal amount of time. So I guess that works. But the fact that planets move faster and slower does not work with this particular model, right? Because in a circular model, the planet would not be changing its velocity, or at least roughly it would be staying the same.
Which they had observations to show that they did
Exactly.
increase.
So observing that, hey, this planet is just straight up moving faster over there and moving much slower over here, you're like, okay, there's obviously some correlation between both of these points. Let's try and deduce it, right? So like that understanding was quite powerful, where he got these first 2 laws. He obviously contributed greatly to motion itself, the planetary motion itself, and to astronomical motion, because a lot of this basically can convey into even like the sun moving around the galaxy. Equal areas, equal time. Kepler's law still hold. The galaxy moving around the galactic supercenter.
Oh,
still
hold
same
on.
thing.
So hold on.
What's that?
I don't think it holds up still.
It doesn't hold up
Because of dark matter.
Okay. If you add, though, that's what I'm saying. If you
Yeah,
take
but-
into consideration dark matter, it would make sense.
But you said it even holds up for the sun around the galaxy, but it doesn't.
Yeah, I guess dark matter is a little bit of a pain in the butt, but
I guess it would theoretically work.
Theoretically, the idea would be able to work for anything, right? That's his idea, that hey, this can be portrayed into any planetary system. So that's his first 2 laws. Takes him 10 years. The next law took him another 10 years to formulate. The third law of planetary motion, and this is the biggest one, right? This is the biggest law that basically relates the proportionality of any body's radius with its period, or with its
You mean the semi-major axis?
well, like, yeah, sorry, I shouldn't say radius because it's not a circle. What am I saying? You're right. You're very right. The semi-major axis. So again, in an ellipse, right? There are 2 axes. So along one of that axes it basically relates that axis to the time period of that orbit, which from there you can almost directly kind of get the equations of motion for these objects, because you're relating the time that it takes for them to move around one time, for the time period, to some unit of length, right? So you can basically
Also, the
get out of this.
mass.
What's that?
It's related to the mass.
To the mass
means
as
if
well.
you know the
So no,
semi-
as I said proportionality.
Yeah,
so the
but
actual equation itself has a lot of these
Oh,
variables into it as
What
well.
I'm saying is that if you know T and A, then you can find the mass.
Oh,
You
that way.
calculate
Like
the
you can
mass.
also backtrack because all these equations are given in these ways. Yes, of course. And again, at the end of the day, as I mentioned, this is a proportionality statement. Like, so it wasn't the equation itself, but in this time when he had invented these three laws, this basically formulated and helped formulate the universal gravity equations, right? Newton was fueled by these very laws. You can derive Newton from these laws, right? And yeah.
Do you remember what that linear graph was with the planets, where it's like the mass or like the semi-major axis versus period, and you graph the planets and they look linear?
I
Was
do
that
remember
it?
something like that.
Was it semi-major to period?
I think it was semi-major cubed to period
Squared
squared,
was linear.
or period cubed, like whatever the relationship. Wait, is it? It's semi-major cubed, right?
Wait, that would make sense though.
Yeah, I'm pretty
That
sure.
would make
Because
sense.
semi-major cubed to the squared is
It's
linear.
a linear.
It's
Yeah,
exactly.
exactly.
So yeah. I mean, as we were just talking, like if I don't know why I just talked to them like they're different, but they fully heard what we were just talking about. But yeah, so that's one observation that I guess you can also deduce from this whole thing.
I think
idea.
actually he noticed that before stating. Yeah, that's how he made his third law. Now I remember. What he did is he got the semi-major axis and the period.
Oh, and then he
And
plotted
he
it,
plotted
and then
it.
he just kept
He
seeing.
saw it was linear, so he's like, "Wait, the period squared has to be proportional."
No, that makes
to
sense.
the,
I think I do remember
Yeah.
something like that because I think that's how we learned it in
yeah,
our
that's how we
astronomy
learned
class.
it too.
Yeah, no, that's actually very
That's
cool.
very
That's
smart.
very cool. That's very cool.
Yeah.
Because if you think about it, if you just plot the periods or like plot any of these two properties of these objects, because I mean, if you just think about it intuitively, the time period, like if you think about like a string, for example, simplest example, the time period of that string that it takes to finish one orbit will depend on the length of that string, right? So I guess from there, if you bring it down to, hey, this radius factor, radius being the semi-major axis factor, and the period are somehow related. So let's just plot a bunch of these things and let's
Yeah.
just see what happens.
And the cool thing
I
about
think
log
it was
scale,
like a guess and check.
I
Yeah.
guess. But the cool thing about log scale plots is that all of the powers become coefficients. And so, if you plot the period versus the semi-major axis on log scale, you're going to find, like, if pretend we didn't know the relationship and we just decided to plot it on log scale, we would see this linear relationship. And then the slope of it would give us an idea of the exponent.
Yeah.
And so you find that like T would be proportional to A, which is semi-major axis. So T proportional to A to the power of 3/2. And then from there you can see it's T squared proportional to A cubed.
That's probably, that's almost definitely what he did.
Yeah, for sure.
Yeah, the log scale definitely sounded like something he would use. That's just gene.
Even though you can't Desmos it, you gotta do it yourself.
Oh my, how do you do that? Log graph?
I mean, people actually, when they would try to,
no.
when you would,
The video's off.
For
Okay, well,
both?
it's audio. Yeah,
whatever.
it's audio. On the video now.
So for both, I don't even know what should I say.
Sorry.
I was talking about like mental calculations.
Mm-hmm.
What people would do is that they would like write down these power tables in log scale. So then you can just relate it back.
Yeah, that's a logbook.
Yeah.
Yeah, that's a logbook.
So,
We had those in
Really?
India because we couldn't use calculators on our exam. We used to have logbooks. Yeah.
That's literally what they did like before calculators. So, you'd have these log tables, and,
Yeah.
and then when you try to like do some exponents, you'd work with the logs instead. And
It's actually pretty genius.
no, it's genius.
It's pretty
but
genius, man.
it's-
Like,
it's
how
genius,
do you
but
think?
yeah.
Like, cause, man, all of these history of physics episodes just really get me thinking into like how I say this every single episode, but it really gets me thinking, man, into how these people were thinking.
Yeah.
So different in a way that you can't even perceive, man. A really famous thing that Kepler also did, like something that I don't even know how you would start to think about, was that the ratio of the inscribed circle to a circumcised circle of any polygon. So take any polygon, draw an
Oh yeah.
inscribed circle and a circumcised circle.
I was like, wait,
Wait,
that
not
can't be the
circumcised.
word.
Not circumcised.
I had a moment. I was
wait.
like,
I'm
what?
forgetting.
Circumscribed.
Circumscribed. I'm so sorry. So inscribed circle and a circumscribed circle on any regular polygon, the ratio of those two circles, the areas of those two circles, is constant. But in any polygon,
That
any regular
cannot
polygon,
be true.
that
cannot
one
be
of
true.
the discoveries of Johannes Kepler.
That can't be true. Imagine a 100-sided regular polygon.
Okay, listen to
How
this.
how is that ratio going to be close to a triangle?
Kepler had an epiphany in 1595. He realized that regular polygons bound one inscribed and one circumscribed circle at definite ratios, which might be, quote, the geometrical basis of the universe.
There's no way that's true. Think about it. A 100-sided polygon, the ratio to the inner and outer circles is going to be close to 1. And if you take a triangle, the ratio from inner to outer is not going to be close to 1.
Okay.
So I don't know about that.
1 second. 1 second.
I think by definite, he doesn't mean constant. He means something else by definite.
Maybe he doesn't mean constant. Maybe he
There's
means
no
like,
way it's constant.
Because
Literally, if
I
you
guess
just
if think
if you
about
just
it-
increase the number of sides, then the circles get closer to each
one
other.
minute. The whole point of calculating pi
Yeah,
was done
yeah.
by the difference in the areas. So it literally can't be constant because the areas of those circles approached pi, or like the r, like when they divided out, like when they knew the
Sure.
radius of it, it approached pi. Oh yeah, you're actually kind of right. So, I think you might be correct there, Barger.
Anyways,
It does say definite. It doesn't say constant. It does say definite ratios. I might have misunderstood.
Oh,
it.
I think like the interesting part about that is that it's not like the ratio is not irrational. Like there's like a number that you can assign to
But
it.
doesn't that just make sense?
I don't know.
Pi r
That's-
squared over pi r squared. You cancel the pi. Like it's a different r, of course. But like
Yeah,
why
but
would it be
maybe they didn't
irrational?
know about
I
like
mean, I guess.
no, they probably knew that pi was irrational.
Yeah, of course they knew pi
No,
was
I know,
irrational.
I know, but then that's not so impressive.
Okay. This was more impressive when I thought about it, I guess, at first. But point that I was trying to make as I started this argument was basically trying to say that these individuals thought in very interesting ways,
Yeah.
right? Like who even thinks about, putting a circle inside and the outside of these polygons? Like even to think about pi
Yeah.
originally, to do that and to keep increasing the number of sides until you get to this level. Like how do you even,
Yeah.
It really puts stuff into perspective, really gets you thinking about what the world of science really entails, man. What we really
Yeah.
need to think, how we need to think.
Well,
So
This-
also, I should mention to those watchers out there, you might have noticed the video is no longer present. So with the abundance of issues here today, we apologize. Did want to mention that with the audio listeners as well. just as after we recorded the episode. It was definitely a fun episode to record, but man, were there problems. Yeah.
Anyways,
Anything else?
no.
Anything else on your individuals that you want to talk about?
Just make sure to follow the podcast on Spotify.
I guess that's the
That's
only
all
thing.
I gotta say.
I mean, why not go on YouTube too? Follow it there too. Why not?
Boom.
You know, go on Instagram too.
Yeah.
Why not follow us there? I mean, Instagram, as I say, all of our updates are always posted there. Like all of the fact that we were late this episode was all posted. All the updates were there. So if you do want to know, if you do want to, you know, be in tune with the Math and Physics podcast, go follow our Instagram.
Right. So yeah, thank you so much for listening to this episode number 90 of the Math and Physics podcast. I'm your host, Parker.
And I'm Ray, and we shall see you soon.
Bye, guys.